Assalamualaikum warahmatullahi wabarakatuh and good day to Dr. Joe. We will now be presenting about our project in railway impact assessment in the main topic of noise analysis. We will introduce ourselves first. My name is Ahmad Faiz bin Hussein.
My name is Anis Shafiqah binti Hashim.
Hello, my name is Muhammad Aziz Fidaus bin Hasnan.
Hello, good day. My name is Norifah bin Nursha.
Hi, my name is Nurhanisa binti Juki.
Assalamualaikum. My name is Ahmad Alif Imran bin Ahmad Iswari.
As for that, now we will start our presentation. Firstly, is my part introduction. The establishment of a good transport network is therefore essential for a city's future growth. High-speed rail have now become an integral part of the transport system, creating new trends for city-to-city travel. LEQ, as also known as equivalent continuous sound pressure level, is constant level that would have the same total sound energy being produced over a given time. LEQ is a fundamental measurement parameter constructed as a single number to describe a changing source of sound over a given time. With this knowledge, we are given a question that can help improve this by design a sound barrier that could help decrease a sound pollution in the area. Sound barrier are help to reduce the noise of the transport in near highly populated area of residents. Next, I will pass it to my friends.
Right now, I am going to talk about the problem. So, for land transport, rail is used extensively. There are significant number of rail signal crossing near to the residential area. Train operators are obliged by the federal law to sound their warning horn while passing at grade crossing. Even so, the train produced very high noise and sound level around the community, which has caused a crisis to the people. The noise that created from the horns and warning signals result more widespread impact. The exposure to loud noise and sound kills the nerve endings in the inner ear. The outcomes is permanent hearing loss, which cannot be resolved by surgery or medicine. The level of sound exposure is an energy measure the level of exposure obtained and the period of exposure. Apart from using sound exposure level, reduce noise, set noise barriers along the railroad is also the solution by blocking the line of sight between a noise source and the receiver. The barrier works, thereby establishing a sound shadow region. And the objective of this project is firstly to identify natural soundscape versus environment affected by human activity. Second, to develop a local evaluation of a traffic signal crossing noise problem close to a protected residential area. Third, to discuss the use of the daily exposure level and insertion loss as an indicator of cumulative effect. Fourth is to determine how FEL or IL of the barrier accumulates from different types of source. That's all from me.
Hello. I will present my part, which is method and formula for the first section. So the formula for first section used is the equivalent continuous sound pressure level. So it is the same equation for the both daytime and the nighttime. So the equation is LEQ for 1 hour will consist of SEL reference for the stationary source, then 10 log to the number of activity, and then log the number of second over 360,600 minus 35.6. So this both is the same formula. Okay, that's all for me.
Okay, next I will talk about the method and formula for section B, which is uh, for ground factor. The first formula is ground factor, soft ground. G, there are three type of the formula called HF. The height of effective path is less than 5. The G is 0.66. If the HF is between 5 and 42, you use the formula 0.5 1 minus HF over 42. And lastly, if the HF is more than 42, the G is 0. Next formula is HF. HF is equal to HS plus 2HB plus 2HR over 2. HS is the height of source, HB is the height of barrier, and HR is the height of receiver. Next is the yellow box, the noise barrier parameter, or P. P is equal to A plus B minus C. A is the shortest distance between the source and barrier. B is the shortest distance between the barrier and the receiver. And lastly, C is the shortest distance between the source and receiver. Next is the barrier insertion loss formula in the red box. Max or the A barrier minus 10 G and B minus GG log D over 50. This is also same as C. Lastly, total shielding design formula in the blue box, L barrier or a building or a trees. Okay, that's all from me.
Okay, I will explain for the result and discussion for the section A, which is the equivalent continuous sound pressure level. So the first calculation is for the daytime LEQ 1 hour. So by using the formula that stated above, for the daytime, we will use the SEL reference of 109 dBA, which is the stationary source for the crossing signal. And then the event, the time of event is 25 seconds, and the number of event for from 6 a.m. to 8 p.m. is 200. So, and then is 12 hours. So the 200 of event divided by the 12 hours, we get 16.67. So input all the data that we got. So we got the LD is 64.04 dBA. Next, we proceed to the night LQ. As use the same formula, but the different data, which is the night event is only 12 and only 10 hour of operation. So 12 divided by 10, we get 1.2. So input all the data and we will got for the night is 52.61 dBA at 50 feet. Okay, that's all for me.
Okay, next for section B. As for the result and discussion for noise analysis, first of all, we need to do some assumption for HS, HR, and HB. The HS, HR, and HB that we assume for this project are 8 feet for HS, HR equal to 5 feet, and HB equal to 15 feet. Then after we do some theorem Pythagoras like this, then we can get the value for the barrier dimension. As we can see here, A equal to 147.81 feet, B equal to 393.83 feet, and lastly, C equal to 541.35 feet. Okay, next. The insertion loss, which are IL design of the barrier. First of all, before we can calculate the insertion, loss or IL barrier, we need to identify effective path head, which is HF, with and without barrier. Both of this calculation use same formula and substitution. Just add HF without barrier for HB, which is height of barrier. We will substitute it with 0. Then here is the answer for with and without barrier. Next is the ground factor with and without barrier. For this calculation, we will use this formula for both because the HF for with and without barrier is at range between 5 to 42 feet. So we will use this formula. Thus, here is the answer, which are 0.93 for ground factor without barrier, while 0.37 for with barrier. Then, in order to determine a barrier, we need to figure out first the barrier parameter with formula A plus B minus C. Then we will get 0.29 feet. As Aziz has explained before, here is the formula that we will use to find a barrier. After we will calculate it, obviously here we see mean, which means if our answer exceeds 15 dB, we will take 15 dB as our answer. But for this case, a barrier for our project is 7.56 dB, which means less than 15 dB. Finally, the IR barrier. As for this calculation, we will take the maximum value as for the final answer for IR barrier. After do some calculation based on the formula, here is the answer that we got, which is 4.87 dB. Okay, then we continue how to calculate total A shielding. This is the formula to identify A shielding. In this formula, we will need IL barrier, A building, and A3. We already calculate and I have explained before for IR barrier. And while for A building, we will substitute A with 0 because the location for our research project, there are no building involved. And for the calculation for A3, we will use this formula. W we will substitute with 100 meter, which is 328 feet. Then we will got 16.4 dB. Since this formula need the answer less than 10 dB, so the final answer for A3 is 10 dB. Lastly, clearly we can see that the final answer for A shading is A3 with 10 dB. It shows that the 3 is more effective than the barrier. Okay, that's all for me.
Okay, hi. So it's my part now. So as you can see, there's the barrier design drawing. So as you can see from the question, we get the source height is much higher than the receiver, but it's lower than the barrier. So based on our research, we assume that the barrier height is 15 feet. So my friends before have already explained about the calculation about how do we got the A, B, and C value. So I will just state it that the A value is 147.81 feet. So the B value is the 393.83 feet, and the C value is 541.35 feet. So that's all from me. Thank you. Next.
Okay. Next, I will talk about the overall design sketching for the whole section B. We can see the distance from the source to the barrier from the ground is 147.63 feet. The distance from the barrier to the receiver from the ground is 393.70 feet. For the thickness of the tree zone is 100 meter, but we convert it to feet, we get 328 feet. And the height of the tree zone is 15 meter, which we convert to feet, we get 49.21 feet. Okay, for the HS and HR and HB, we already assume from the previous assumption, which is HS 8 feet, HR 5 feet, and HB is 15 feet. For A, B, and C is also we already calculated from before, which is A is 147.81 feet, B is 393.83 feet, and C is 541.35 feet. Okay, that's all from me.
Okay, so as for the conclusion for our report, so for section A, we get to calculate the LEQ for both daytime and nighttime. So the daytime LEQ is 64.04 and the nighttime LEQ is 52.61. Why? Because in LEQ for the day is why is higher, because the event on daytime is much more than the event on the nighttime. So based on that calculation, we calculate the design insertion loss per barrier to know the cross-section barrier source and receiver. It's better to sketch the sound travel. So based before on the calculation, the insertion loss of barrier we get is 4.87 dB, assuming the height is of barrier is 15 feet. And because from the assumption we get to calculate the ABC by using the Pythagoras theorem. And then the attenuation. The attenuation, based on the attenuation, based on the calculation and the results, we need to use the maximum dB. So which based on the result, the maximum is from the tree. So therefore, we use the 10 dB because the total shielding is the maximum for the barrier. So as the conclusion, we can calculate the noise exposure from the railway in design, the adequate noise barrier from the noise exposure data that we acquired before. Thank you.